Okay, so we're very happy to have the second talk for today by Chris Hull. Chris visited us in 2020 as well. We're happy that he's back. And so today he's going to tell us about charges and duality in gravity. Chris, please.
Great. Thanks very much. It's very nice to be back. So I'd like to thank, like the others, to thank the organizers for inviting me. Here's a snap from a picture I took last time I was here. So what I want to talk about today is some aspects of which may give some insight into the nature of M theory. In particular, I want to look at some of the magnetic aspects of gravity which M theory tells us about. In particular, I want to talk about some of the magnetic phenomena in gravity which are associated with Kaluza-Klein monopoles. And one of the intriguing things is that we learn from M theory is that there's an important role played by Kaluza-Klein monopoles, which in some ways are very closely related, are very analogous to branes, but they have some interesting and strange differences. And I want to relate some of this to some work I did some time ago, looking at a particular possible limit of M theory, which is related to the 2-0 limit of Yang-Mills, which Neil talked about the other day. And this gives a possible exotic phase of M theory in which gravity is described rather differently, in which, in particular, the electric and magnetic structures of gravity are intimately related via a kind of generalized self-duality. So why isn't this? Oh, there we go. Okay, so I've got. So thank you very much. With that, I conclude my talk. How do I get back to? Okay. So as we've just seen from those slides, but having after all that, let me just go back to the beginning. Just some elementary ideas. If we look at gravity reduced, Kaluza-Klein reduced on a circle from d to d-1 dimensions, as is well known, the metric gives rise to a metric of Kaluza-Klein vector field, a graviphoton, and a scalar. And in particular, the momentum splits into a lower dimensional momentum, and the extra component of momentum is associated with the electric charge for the graviphoton. And there's a magnetic charge, which is the d-5 form in d-1 dimensions associated with this. And this has an origin in d dimensions from a gravitational magnetic charge, which is a d-5 form in d dimensions, whose dimensional reduction gives rise to the magnetic charge for the graviphoton and the gravitational charge reduced down to by one dimension. So, for example, if we went from 5 to 4 dimensions, then the magnetic charge is in 4 dimensions is just a scalar. It's a d-5 form, which would be a naught form, and this would arise. From 5 dimensions from a naught form in 5 dimensions, which dimensional reduction would give rise just to the magnetic charge in 4 dimensions. So we have this charge K, which is naturally arising in gravity, and this is the charge which is carried by Kaluza-Klein monopoles. And what I want to investigate, one of the themes of this talk is to investigate, say a bit more about this charge. So this charge arises in the supersymmetry algebra. For example, in 11 dimensions, there's a 5-form charge which occurs in the superalgebra. If I split these space-time indices into 10 spatial indices labeled by I plus the time component, this has got the usual M5 brane charge, but then there's a charge which is a 4-form in a spatial 4-form, which is the dual of a spatial 6-form, and this is the gravitational charge I've just been referring to. So it's this magnetic charge we'll refer to here today as a K charge appears in the algebra of conserved charges, and so is a conserved charge. The magnetic charge for gravity in 5 or higher dimensions. So it's an interesting feature that is a feature of gravity which is not seen in 4 dimensions, but is an important part in 5 and higher. I calculated the form of this from the superalgebra, and I'll give the expression in a moment, and it gives the correct BPS charge carried by Kaluza-Klein monopoles. So just to give a brief flavor of the form of it, if we look at an asymptotically flat matrix, so we have a space-time which is asymptotic to Minkowski space, which I'll renote as G bar, then we have the difference between the full spin connection and the background spin connection is a difference of connections, and so is an asymptotic tensor. And if we have an asymptotic killing vector for the metric, the background metric has got killing vectors, the translational and rotational killing vectors, and if you take one of these killing vectors, then we can construct a corresponding charge, as was done long ago by Arnowit, Desser, and Misner. So in particular, if we take the translational killing vectors, then the corresponding charge is given by integrating over a d-2 sphere at spatial infinity, and it has this, can be written in this form, which is covariant, given that this is an asymptotic tensor. So particularly if we chose the time-like killing vector, this would give the ADM mass. If we chose a space-like one, it would give the ADM momentum. And for the K charge, if we take a asymptotically constant d-5 form in or a constant d-5 form in the background Minkowski space, the corresponding K charge could be as a d-5 form. So if we dot it with this constant form, we can write it in this way, where rho here, strictly speaking, is an eddy form which tends asymptotically to this, and we get this form for the charge. And so here in this form, you see that it's rather similar in form from that of the ADM charges, but there's one difference is there's a Hodge dual in here, but there's not in here. So it's a natural form you can write down, a natural object you can write down using the same ingredients that came in from the ADM charge. So what is the meaning of this charge? It's some sort of dual charge for gravity, and in the linearized theory, as I want to argue, it could be thought of as a magnetic charge for gravity, which could be thought of as an inerted charge for the dual of the graviton, which is the so-called dual graviton. And one of the questions we can ask about, given the role of this, is what is the spectrum of states which carry this charge, and are there any other magnetic charges which are relevant? Because states carrying this charge can be BPS, it's an interesting question about what is the BPS spectrum of the theory. And in a number of approaches, for example, looking from the point of view of exceptional generalized geometry or exceptional geometry or E10 or E11, naturally give rise to various dual graviton charges which have got charges which are associated with Hooke-Young tableau. And I wanted to say something about what is the role of these charges, what are they to be understood as, how do we understand them as topological or as Noether charges? So that's one of the themes of this talk, and I also want to talk about some of the relationships of this to M theory and wants me to stay here. There we go. To what is the nature of M theory and what it tells us about gravity. So it's related to the question about what does M theory look like at energies much higher than the Planck scale. It's long been conjectured that at ultra high energies there could be a much more symmetric phase of M theory or string theory, and there might be some sort of phase transition to a stringy phase. Recently there's been some very interesting progress in that direction, for example in three-dimensional anti-de Sitter space, where such a stringy phase has been proven to exist. So I want to look at a slightly different place, which is related to some work I did some time ago, which is looking at M theory compactified on the 6 torus, and the conjecture that it has at ultra high energies, it gives rise to a 6-dimensional theory which has got 4,0 supersymmetry, which is highly supersymmetric, in particular would give a conformal theory of gravity without higher derivatives, and would give an exotic theory of gravity without, is based not on a fundamental metric. No, I mean, if I start off in 11, I go down on T6, which would take me down to 5 dimensions. And so I have a 5-dimensional theory whose low energy limit is 5-dimensional supergravity. And then I look at a strong coupling limit of that, and then the claim is that an extra dimension would open up, which is unrelated to any of the dimensions which are in the T6, and would give rise to a 6-dimensional theory with 4,0 supersymmetry. So I'm going to say a little bit more about the details of how this works in a moment. Yep. Yes. So not the Lorentz generators, but I will say I'll answer that. That's one of the questions I want to answer in this talk. So I want to say a bit more about this motivation, and then later on in the talk I'll come back to precisely that kind of question as to how one understands that. So that's one of the questions I was setting up. What is the nature of this charge? What does it do? Why haven't people talked about it more, perhaps? A reminder, so if we look at the 5-dimensional superalgebra with n supersymmetries, there are various central charges. There are ones which are antisymmetric in these indices where A runs from 1 to n, and there's a scalar central charge. So the superalgebra takes this form. The details of how the spinors and so on work, C as a charge conjugation matrix, are not important here. The important thing is that the BPS states can carry either these charges or this charge X. And these Zs are electric charges for the Maxwell fields. For n equals 4 super Yang-Mills, this charge X is carried by the certain solitons in the theory, which are given by taking a Yang-Mills instanton in R4, a self-dual Yang-Mills configuration, and then lifting this to 4+1 dimensions so that the point-like center in 4 dimensions becomes a line in 4+1, a time-like line in 4+1 dimensions. And so this is interpreted as a soliton in 4+1 dimensions. You have a localized core, which has a time-like evolution to look like a sort of a solitonic particle, and I refer to these as instantonic solitons. And these such objects are BPS and carry this charge x. And in n equals 8 supergravity, x is the charge I was referring to as the k charge, and we'll say more about that in a moment. So in 5-dimensional Yang-Mills, the Z's, the electric charge is spontaneously broken. These are the electric charges carried, for example, by the W bosons. And the Yang-Mills instantons lift these naught branes with x proportional to the instanton number. And these BPS states are in massive tensor multiplets, where you have a two-form satisfying in 5 dimensions this massive self-duality condition, where this mass is related to the is given by the central charge, which is given by the instanton number, which is an integer, divided by the Yang-Mills coupling squared, which is dimensionful in 5 dimensions, and some 2 pi's, which 2's and pi's, which I'm suppressing. And so these become massless as the Yang-Mills coupling tends to infinity. So this is a bit like what happens for the D0 branes in 10-dimensional supergravity, in 2A string theory. They become massless at strong coupling, signaling the opening up of an extra dimension. So here we have a spectrum of particles which coincides with that of a Kaluza-Klein tower for a 6th dimension of radius given by the Yang-Mills coupling. So at strong coupling, you have a decompactification to a 6th-dimensional theory. And this 6th-dimensional theory has 2, 0 supersymmetry. And that follows from the sort of multiplets that these massive tensor fields fit into. The 5-dimensional super Yang-Mills theory is non-renormalizable. So we think about this story as being embedded in an ultraviolet complete theory. So my proposal was that a similar thing could happen for gravity. So if we look at n equals 8 supergravity in 5 dimensions, embedded in an ultraviolet complete theory, for example, in theory on T6, if there are BPS states which fit into the BPS states satisfying this, carrying this charge k, would fit into multiplets with a massive 4-index tensor field. And if there are such states and they have a spectrum which goes like this, given by an integer divided by the 5-dimensional Planck scale, then these would become light as the 5-dimensional Planck scale tends to infinity. And if we have this spectrum, then this would be just what was needed for this to be a spectrum of Kaluza-Klein states, and for this to be a decompactification to a theory in 6 dimensions. And so we'd get a 6-dimensional massless multiplets, which involves some higher dimension, some 6-dimensional origin for this 4-index tensor field. And there's a unique such multiplet which comes out, which is one which has got 4, 0 supersymmetry and is in fact a conformal multiplet. Yes, I'm going to comment on that in a moment. Exactly. Yep. Yeah. No, so I was talking about the story going from 6 to 5. When you go from 6 to 4, then you get the story I had on each of the dimensions, and then you get, and that gives rise to the S-duality. Interchanging the two gives rise to the S-duality, which interchanges the electric and magnetic charges. Yeah, and so a lot of what I'm going to talk about, I'm going to concentrate on the going from 6 to 5. There's a very interesting story which emerges when you go from 6 to 4, and it gives a very important six-dimensional origin for S-duality for the Yang-Mills. It's also very interesting for gravity, but I'm not going to talk about that today, but it's an interesting point. So, there are free theories in 6 dimensions with 2-0 and 4-0 supersymmetry, and the 4-0 multiplet is, in a precise sense, a square of the 2-0 one. So in a sense, it's a double copy. You can understand the free multiplets precisely that way. The free 4,0 multiplet consists of, looks like a lot like a supergravity multiplet, but with extra space-time indices. So in the 2-0 case, instead of having the Yang-Mills is replaced with one index, is replaced by a 2 form with 2 indices. Here, the graviton with 2 indices is replaced by a 4-index object with 4 indices. This has the Young tableau. This has the symmetry properties of the Riemann tensor, and I'll comment on that in a moment. The gravitino has, instead of having one vector index, has got 2. The vector field, instead of having one index, space-time index, has got 2. It becomes a 2 form. And then there are fermions and scalars. And reducing on a circle gives rise, for the 2-0 case, gives 5-dimensional Maxwell theory, and for the 4-0 case gives linearized supergravity. I'll say a bit more about that in a moment. So the graviton and the vector field come from these higher tensors, and the key thing is that both of these have got self-dual field strengths, which is why they don't give more higher spin objects. For both of these theories, there's no conventional field theory interactions which could be written down for these theories, which are local and covariant. But nonetheless, for the 2-0 theory, we have strong reason to believe that an interacting 2-0 theory exists, which is some non-Lagrangian conformal field theory, which remains mysterious, but nonetheless reduces to 5-dimensional interacting super Yang-Mills. And so a key question, a very interesting question is, does an interacting 4,0 theory exist, reducing to 5-dimensional supergravity? So in the context of the double copy question, which was asked, we could think about think about the constructing amplitudes for the 4,0 theory from a double copy, essentially a sum of squares of 2,0 amplitudes. And so in principle, understanding the 2-0 amplitudes would tell us, would immediately give us a proposal for what the 4,0 interactions should be. And rather remarkably, this would give a theory in 6 dimensions which is conformal, but nevertheless reduces to gravity in 5 and lower dimensions, conventional gravity in 5 and lower dimensions, and which is based not on a metric, a conventional 2-index graviton, which can be understood geometrically, but this as an exotic tensor instead, which is rather interesting. So let me just give a little bit of the details about how some of this works. So I mentioned that the 4-index object has got the symmetries of the Riemann tensor, so it's antisymmetric in pairs, and you can interchange the pairs, so it corresponds to this Young tableau. It has gauge transformations which have a parameter which has got 3 indices. You take one derivative of this object and then project onto this Young tableau. And the corresponding invariant field strength is one where you take two derivatives of this and then symmetrize to give this Young tableau. And it's required to be self-dual on both the first three indices, or the first column, and on the second column, which I write symbolically this way. So the first of these is explicitly given by this. So if we consider the analog of a self-dual B field giving rise to magnetic duality, if we think about a normal two-form in 6 dimensions reduced to 5 dimensions, it gives rise to a 2-form and a 1-form, where the 1-form is given by the components where one of the indices is in the internal direction, and the corresponding field strength splits into the field strength for B and for A. So normally this would give rise to 2 different fields, but if in 6 dimensions you have the self-duality constraint, then this implies that the field strength H is the 5-dimensional dual of the free-form H is the 5-dimensional Hodge dual of the 2-form F. In this way, it's saying that in 5 dimensions, A and B are electromagnetic duals, and we can think in the free theory as these giving alternate formulations of the free theory. So we could eliminate little b in terms of A, for example, and so we'd get a Maxwell theory in terms of A. And, or we could instead write it in terms of B, and we get dual formulations of the theory. So there's a similar story for the gravitational field. It reduces down to a 4-index, a 3-index, and a 2-index object, depending on how many of the indices are in the 5 direction. And the corresponding field strength split into the field strengths for these objects. In each case, the field strength, you add 2 boxes and symmetrize. You add take 2 derivatives, the corresponding field, and then symmetrize. And the self-duality constraint implies that this field strength is dual to this one, and this one is dual to this one. So they're all dual to each other. So it implies that the 3 fields that you get here are all dual formulations of the graviton, the linearized theory, that this is the dual this is what I call the dual graviton, and this the double dual graviton. And these, in the linearized theory, give alternative formulations of the free theory, written in terms of D or C. Now, one of the features is as one goes from one formulation to a dual, as it interchanges field equations with Bianchi identities. So for the photon, we have the dual of a photon in d dimensions is an n form, where n is d minus 3. And for a graviton, we get the dual graviton or the double dual graviton, and where one or both of these boxes are replaced by a column with n indices. And as I mentioned, the duality interchanges field equations to Bianchi identities. And if the 4, 0 limit exists, then there's a number of things one can say. First of all, when we're talking about the strong coupling limit of the 5-dimensional supergravity theory, strictly speaking, because this is a dimensional parameter, a dimensional parameter, what we're really talking about is limiting one where we're going to energies which are much larger than the Planck scale. So the limit is really one of going to trans-Planckian energies. Just as in the 2-0 theory, in the Yang-Mills theory, we're going to energies much larger than the Yang-Mills scale. And so this highly symmetric superconformal phase would be emerging at trans-Planckian energies. It's got, as well as the 32 supersymmetries you'd expect, it's also got 32 conformal supersymmetries fitting into this large superconformal group, with the graviton arising from this exotic tensor, giving an exotic theory of gravity. And a key question is whether there's a 4-0 phase of M theory. And so a key question here is whether there are states in M theory compactified on T6 which carry this charge K, and secondly, do they fit into a Kaluza-Klein tower? And so this gives a test which can be asked within M theory, which is whether there are BPS states of this form which carry this charge, and secondly, whether they fit into a Kaluza-Klein tower. And that's I'll talk about a bit more. And so that's one of the reasons why I wanted to focus on the nature of this magnetic charge K. So a key feature of this is whether or not there are M theory has states which are magnetically carry this gravitational magnetic charge. So if we're looking at momentum modes on the circle, these become naught branes in 5D, so that the 5-dimensional theory should have naught brane solutions corresponding to these. The interacting 2-0 theory gives 5-dimensional super Yang-Mills, and the Kaluza-Klein modes are identified with these instantonic solitons I've mentioned. And in the free 2-0 theory, we can do the reduction explicitly to get super Maxwell theory. But in this limit, the instantons become zero-size singular instantons, singular solitons in the Maxwell theory. There are various ways one can regularize these. For example, the way that Neil did it with David Tong would be you can find non-singular solutions by adding an electric charge to these. You can also desingularize these by going to a non-commutative setup. Or by embedding in the by embedding in the non-abelian theory, which would give a non-abelian non-singular core. For the free 4,0 theory, one could do the reduction explicitly, get linearized supergravity, and the Kaluza-Kleins in the free theory can be associated with singular solutions in the 5-dimensional free theory, which can be thought of as a zero-size gravitational solitons associated with 5-dimensional with singular gravitational instantons, the analog of the in this construction of the instantons in the Maxwell theory. And so there are if there are, as usual, there's a question about whether there are really are BPS states which carry these which associated with these singular solutions. A lot of this BPS states we've gone to know and love in M theory as in fact associated with singular supergravity solutions. So given a singular supergravity solution, there's a question about whether there's a corresponding brane in the theory. Yeah? Okay. Depends what your question is, really. But I do, and that's what I'm going to tell you about. Yes, thank you. As Neil anticipated, there's a question about what these, interesting question about what these objects are. So does the nonlinear supergravity have suitable naught branes? The Kaluza-Klein modes would have the multiplet structure associated with a self-dual 4-dimensional space times time. And so a natural place to look at is a gravitational instanton. So I'll look at, for reasons we'll see in a moment, I'll look at this so-called Givens-Hawking ansatz. So I'm looking at a space in 5 dimensions, which is given by a 4-dimensional Euclidean space times time. And here's the 4-dimensional Euclidean space. Could be thought of as a fibration over R3 with some points removed. So you have a scalar on R3, which satisfies a Laplace equation with possible sources. And A could be thought of, this vector field could be thought of as the 3-dimensional dual of the scalar. related in this way, and F is the curl of this A. And the Kaluza-Klein monopole is this times time, and this is the famous Kaluza-Klein monopole solution. And if we have a single center solution, we have V is 1 plus U, where U is n divided by the distance between U of x is the distance between this and the location of the center x0. And this is, in this case, this is, when n equals 1, this is self-dual Euclidean Taub-Nut space. So here's the metric again. So is this a sort of suitable naught-brane solution for 5-dimensional supergravity? And so for that, we'd require it to be asymptotic to 5. We would probably presumably require it to be asymptotic to 5-dimensional Minkowski space. After all, that's what we require from the Kaluza-Klein modes from reduction on a circle. So there are two problems with this metric. One is it has a singularity at x at the center, an apparent singularity. And the second is it has Dirac string singularities associated with this vector potential, which could be, if we, for example, if we chose A to be of this form, it would have either choices would have a Dirac string. And of course, the positions of the Dirac strings could be moved around by diffeomorphisms or gauge, which are associated with gauge transformations for this vector field. And indeed, the curvature only depends on the field strength of A, not on A directly. So there's a well-known solution to this, which is probably familiar to most of you, that if we require n to be an integer and we take y, the coordinate y to be periodic with this period, then we can construct a manifold with two patches, one with A plus and one with A minus. And this constructs, in each patch there is no Dirac string. And moreover, the singularity at x equals x0 is absent if n equals 1. And for higher n, there's a relatively innocent orbifold singularity. So for n equals 1, we get a smooth, complete manifold, which is a circle fibration over R3, which is a self-dual Taub-Nut, which is asymptotic to a hot fibration over S2, giving us, so at infinity, you get a squashed 3-sphere. So returning to these questions, if we wanted an asymptotic to 5-dimensional Minkowski space, we'd require a non-periodic y. We'd require y to be a non-compact coordinate. So we'd be forced to confront the Dirac strings and the question about whether they matter. And so there's a question about, can we really think about this solution without compactifying the coordinate y? Yeah. So now I want to switch back to the original question about the nature of these magnetic charges and the question about about states carrying these charges. For gravitational charges, for gravity, the gauge symmetry is that of diffeomorphisms, and the isometries are a subgroup preserving a given configuration generated by killing vector fields. So for Minkowski space, we have the Poincare group, and the isometries can be thought of as a global symmetry group for this space-time, and there are associated Noether charges giving rise to conserved charges given by the integral of, for example, this current over a spatial hypersurface. And these can then be used to rewrite the integral as an integral over a sphere at spatial infinity. And this works for spaces with Killing vectors. But a general configuration doesn't have isometries, and so there are no conventional Noether charges. But nonetheless, if it's asymptotic to a space which has got isometries, then you can construct charges at infinity, integrals at infinity, involving asymptotic Killing vectors, giving rise to the generalized Noether charges. And these can, again, these are written as integrals over spheres at spatial infinity and require certain suitable boundary conditions. So asymptotically flat spaces, you get the familiar momentum and angular momentum defined in general relativity in that way. So we can now think about what happens for linearized gravity. We're linearizing about Minkowski space. And there, here we have the linearized Einstein tensor. And we have these linearized gauge symmetries. And so if we have a linearized Killing vector, in other words, a Killing vector of Minkowski space satisfying this, then this leaves the configuration invariant. And so all configurations have an isometry generated by such a Killing vector. So now there are real Noether charges associated with that, which can be thought of as a linearization of the ADM charges. Or conversely, one can think in a very precise way of the ADM charges as arising from integrating up the linearized construction. Been a lot of beautiful work on that understanding, which I won't talk about today. So for a given configuration, so for general gauge theories, we can talk about the analog of the isometries, invariances, gauge transformations which leave a configuration invariant. And there are corresponding Noether Killing gauge parameters and Noether charges. And in general interacting theories, general configurations will have no such invariances, but if it's asymptotic to ones with such invariances, one can define ADM-type charges, and linearizing, these arise from linearizing the gauge symmetry about that configuration for which these are Noether charges. So in other words, the whole story for ADM, the ADM story for gravity generalizes to other gauge theories. So just quickly, if we look at an antisymmetric tensor gauge field with an n-form gauge field with field strength F, there's an electric current, which is an n-form, and a magnetic current, which is the d minus n minus 2 form. And these are both conserved. If the magnetic current is 0, locally we can write in terms of an n-form potential, and we have this gauge symmetry. And in general, this will be reducible. And we can look for Killing parameters, which are n-1 forms, gauge parameters which leave the invariance in the theory invariant. Here, these would just be the closed forms. And because the exact forms don't act, we're really looking at a cohomology. So the isometries correspond to cohomology classes. And we have one-form currents, which can be written in this way, which are conserved, and the conserved charge, and so there's a conserved charge corresponding to each cohomology class, which can be written in this way, and we get a form of the familiar electric charge for this object. On the other hand, if the electric current was 0, then locally we can write it in terms of a magnetic potential with a gauge symmetry, and again, there's an analogous statement which gives rise to magnetic charges corresponding to these cohomology classes. Yeah? So let me. I'm going to talk about this in a. So let me just talk about this slide, and then I'll, which I think will partly address your question. So if we. I mean, there's a sense in what I'm doing can be expressed in that language. So in the general story, where you have both of these sorts of sources, we could also talk about these charges remain conserved, provided these sources have compact support. And these are no longer Noether charges, because in this case, we no longer have these gauge symmetries, although we do have them asymptotically. If the magnetic current is 0, then this one is a Noether current for this symmetry, and this is a topological or magnetic charge. And if the other one is 0, then there's a similar story, but with these interchanged. And these charges are both topological in the sense that they depend only on cohomology classes, F and star F. So the invariances I'm talking about are gauge transformations, which are parameters which are closed but not exact. And so they can be thought of, they're sometimes referred to as large gauge transformations. So we can think of, so this gives us a way of understanding the charges for gravity. If we look at linearized gravity, there's a gauge symmetry like this. There's corresponding, and so the linearized killing vectors satisfy this, and this gives rise to corresponding Noether charges we've seen. But there's also a dual formulation where we write it in terms of the dual graviton. This formulation, in fact, has got two different gauge parameters. It's invariant under two gauge transformations. This has got a Hooke-Young tableau, and this is an N form. And the corresponding field strength is invariant under both of these. And so there's two types of Noether charges, Noether symmetries, two types of symmetries, and so two types of electric Noether charges for this theory. So the analog of the isometries is if these parameters satisfy these generalized killing conditions, that the gauge transformation is 0. So we get a generalized killing tensor here corresponding to the alpha transformations, and here we get something which is known as a killing Yarnow tensor. And for each of these killing tensors, we get a corresponding Noether charge of this kind. And a particular case of these generalized killing tensors is one where we have a metric times an n-2 form, where we have a closed n-2 form. And in this case, this gives rise to a particular Noether charge, which is the linearized K charge, and depends only on the cohomology class of rho. So in this way, we see that the K charge arises as one of the kinds of Noether charges which exist for this dual graviton. And the gravitational duality interchanging the two forms of gravity interchanges the the field equation with the Bianchi identity for the dual theory, and vice versa. Here we get the field equation given by the analog of the Ricci tensor given by a single trace of this. And we can introduce sources for both of these for this field, which involves couples to the generalized Einstein tensor, which is identically conserved. So introduce a source, which is the dual stress tensor, and if this is non-zero, it gives a regular graviton, but Dirac strings in the dual graviton, and vice versa. So in regions with this is 0, we can write the theory in terms of, if the stress tensor is 0, we can, so I've got this the wrong way around. In regions where U is 0, we can write in terms of the graviton, and in regions where the stress tensor is 0, we could write in terms of the dual graviton. And so now we can look at the linearized Kaluza-Klein monopole solution, which is a superposition of where if we think in terms of the linearized metric, we have, here I'm looking at, so I'm looking in suppressing all but 5 of the dimensions. And we can think of it as a superposition of two solutions, because it's a linear theory. You have a superposition story. One is where HYY is given by minus U, and Hij is given by U times delta Ij, where U is m over r, where r is the radial coordinate in 3 dimensions. This looks a lot like, this is the same U we had in the nonlinear gravitational instanton. And this corresponds to having a delta function source for T mu nu. And the other one corresponding to have a delta function sourced for the dual graviton. And in this case, we have H is given by A, where A is the vector field which is dual to a scalar which is n over r. And here, the theory is the solution is BPS if these quantities m and n are equal. So here we have what I just had on the last slide, the linearized Kaluza-Klein monopole solution. We could dualize this part of the solution to get a dual graviton, where the dual graviton is given by W, where W is the dual of the electromagnetic, the scalar dual in 3 dimensions to this vector field. Or we could dualize this one to get the dual graviton given by a vector field and a symmetric tensor, where these are the single dual of B of U, or the double dual of U in this way. So in this way, we can dualize either of these two parts of the solution. So here we have both of the duals in, and so there are Dirac strings as usual for A and B, but each part of the solution we could rewrite without a Dirac string by dualizing. So this one written in terms of H doesn't have a Dirac string, and this one written in terms of D doesn't have a Dirac string. So we have the linearized solution is a superposition of an electric and a magnetic solution. The mass, so M is the mass for the electric solution, and N is the K charge for the magnetic part. And each one has a Dirac string in one duality frame and not in the other. And the positions of the Dirac strings can be moved around by gauge transformations. For the magnetic solutions, forms of the solutions, one can choose 2 patches in the usual way with a transition function given in this way. And so here we have a transition function involving psi y, which is an angle. This is okay locally, but globally problematic because phi has to be periodic. So this would be, so here we're looking at the transition functions written in terms of the gravitational vector field, the vector field gauge parameter. However, this would be okay if we allowed generalized gauge transformations, which in the sense of Yang-Mills, it would be ones which could be sometimes referred to as large gauge transformations, delta A equals alpha, where d alpha is 0 and closed but not exact. So if we allow patching conditions involving these large gauge transformations, then this would be allowed. So where does this leave us? So for the free 4,0 theory, it compactifies to linearized 5-dimensional supergravity. The Kaluza-Klein modes can be associated with the linearized Kaluza-Klein monopole. The Dirac strings, it has Dirac strings in some duality frames but not others. And the singularity at the origin is representing the presence of a particle, so that's not so bad. In the nonlinear theory, the a candidate solution would be given by a Gibbons-Hawking metric for x non-zero. If we interpret these as I've suggested as ones in, with a non-compact coordinate y, then there are necessarily Dirac strings which may not be so bad. It may just be, as we've seen, signaling the wrong use of the wrong variables. In particular, it's signaling the fact that the graviton is not fundamental in this picture, but it's really this higher dimensional 4-index field which is the right variable. And the singularity at the position is associated with the position of the particle. So again, that's similar to many of the BPS states in M theory. And one might hope to resolve this by the lift giving rise to a core, a non-singular core, where you've got this enhanced symmetry phase. So I'm just about out of time, so let me conclude and say where this leads us. So one of the things I've discussed is the new magnetic charges which arise for linearized gravity, which can be understood as Noether charges for dual isometries of the dual graviton. It includes the linearized K charge which occurs in the supersymmetry algebra, plus other charges which don't occur in the superalgebra but are of interest and have appeared elsewhere. And this extends to the nonlinear theory in an interesting way. I've talked in the second part of the talk about the linearized K charge, but at the beginning I gave the full nonlinear form of the K charge. So that one we already know extends to the full nonlinear theory. The interacting theory for the interacting 4,0 theory, this would need a Kaluza-Klein tower of K-charged BPS states in 5-dimensional M theory, or M theory compactified to 5 dimensions. So this provides a very non-trivial test which can be asked within M theory about whether such a theory exists. And so it's asking an interesting question about what is the BPS spectrum of M theory. Are there any, in particular, are there any BPS states other than the ones we usually talk about? Are there any that have been missed? If we can show that there are no such states, then, or there are states but with the wrong spectrum, then my conjecture that there's a 4-0 theory would be ruled out. So these states are U-duality singlets in 5 dimensions, so duality doesn't help. One of the ways we usually get evidence for BPS states that we're not sure about is by having them being related by dualities to ones we do know about. It would have been nice if this story had led to a non-singular soliton as it does for Yang-Mills, but it's not essential. And as I've stressed, often BPS states don't correspond to often correspond to singular solutions. For example, the D0 brane corresponds to a singular solution of 2A supergravity. The analysis of the linearized theory suggests that the direct strings may be tolerable. The curvature doesn't depend on them, and may just be a symptom of the fact we're using the wrong variables. Familiar states will have direct strings if we use the wrong variables. So for example, if one looks at the M5 brane supergravity solution, it has direct strings for the 3-form potential. If we so a singular 5-dimensional solution would be okay if it's resolved in the full interacting 6-dimensional theory. So if the analog with M theory is where the Kaluza-Klein modes are the D0 branes which I've just mentioned, which are singular solutions, but the singularity is resolved in 11 dimensions where these correspond to non-singular 11-dimensional solutions. So BPS states in M-theory correspond to give rise to supergravity solutions, which tell you about the field configuration at large distances from the source. If the solution is non-singular, then the supergravity solution is strong evidence for the existence of a BPS state. However, if it's singular, then you need further input to understand whether the state actually arises. So irrespective of whether or not this limit exists and whether there is really such a 4-0 phase arising at strong coupling, this whole story has had a lot of interesting spin-offs. It's given rise to the notion of gravitational duality, of the dual graviton and the double dual graviton, at least in the linearized theory, and gives an understanding of these magnetic charges. The magnetic charges in gravity arising from the Noether charges for the dual theory. And these I think are very interesting in their own right, and they may have they are likely to have interesting consequences, especially in gravity for d greater than or equal to 5, and especially since Kaluza-Klein monopoles are important examples of states which carry these charges. So thank you for your attention.
Questions for Chris?
Hi, thanks for the nice talk. So typically, when we think of electromagnetic duality, for example, in E&M, when we are forced to go to a phase where we think of the magnetic photon, then there is a direct quantization that tells us that the original gauge coupling was large. Is there a similar story here? Is there a precise sense where when I'm forced to look at these dual gravitons, or when this Dirac string is present, that somehow the gravitational theory is strongly coupled?
Yes, thank you. So there is an analog of the quantization condition of electromagnetism which arises here, which leads to a quantization of this magnetic charge for gravity, which we can think of as being something which relates mass times the magnetic charge being given by an integer. So as usual with the magnetic charges in sort of gauge theory, for example, one can think of it in two ways. One which satisfies the direct quantization condition, the other where it depends on how you normalize things, the other where the magnetic charge is an integer related to a topological winding number. That's the picture I'm looking at, where these numbers are coming out as integers. But the fact that the BPS state condition is relating the mass to the charge is consistent with that condition. And these charges, these magnetic charges, are associated with integers, so that there is a quantization condition associated with these, which is related to the charge quantization for the magnetic monopole, for the Kaluza-Klein monopole, for example.
Great. So then a follow-up to this thing, well, two questions. What picks the different duality frames? Because there are two other, unlike E&M, where there is two duality frame, here there are two additional graviton sectors. So when do I pick one versus the other? Is there...
Yeah. So that was one of the things I was referring to. So in electromagnetism, if you've got no magnetic charges, then you use the electric frame where you write in terms of an electric potential. If there are no electric charges, then it's natural to use the magnetic frame where you write in terms of a magnetic potential.
That's right.
So it's a relation of what kind of sources there are. So there's a question about whether you have, in the gravitational theory, the electric sources is ordinary energy momentum. If that's zero, then you could use in the linearized theory, you could use the dual formulation. If it's non-zero, then you would want to use the original metric formulation.
But you have two dual formulation, not just one, right?
Yeah, so it's
how do you-
so the story is a little more complicated because it turns out that the source for the double dual graviton is algebraically related to the source for the original graviton.
Okay.
So you've got three you've got a triality of formulations, but only a duality of sources. So the story is a little more complex than than I was able to go into. But there's a well-defined story as to what can happen. So that means that, for example, if so there are two kinds of sources. One I called T mu nu, and the other was this higher tensor U, which was the sort of the dual object. So if U was non-zero and the stress energy tensor was zero, then you'd formulate it in terms of the dual graviton. And if it was the other way around, if U was zero, then you could formulate it into, and if both sources were zero, you could formulate it in either the terms. If all the sources were zero, you could use all three formulations. If U was zero, then you could use either the original formulation or the double dual formulation. So in the linearized theory, at least, and we don't have in the nonlinear theory, we don't have any formulation, any dual formulations, either for Yang-Mills or for gravity. So.
Yes. Have more.
Chris, I have a question about these duality invariant gravitational magnetic charges.
Yeah.
Since they are duality invariant, do you expect that they will contribute to the entropy of some gravitational solution in higher dimension, in dimension larger than 5?
Because they're extended charges in larger than 5, these would contribute in principle to brane solutions, but not to black hole solutions.
Yeah, I mean, especially extended black brains entropy.
Yeah, but if one goes down to low enough dimensions, then black hole entropy is, for example, is expected to have, I think is known to have contributions from, for example, degrees of freedom associated with Kaluza-Klein monopoles. So,
but they would result like standard electromagnetic charges in lower dimension. So
yes.
Yeah.
I mean, but their understanding. I mean, some of the charges which we incorporate are ones which are associated with Kaluza-Klein monopole charges. So.
So essentially,
but I think the answer is there are BPS states carrying these charges, and BPS states carrying these charges would and should contribute where relevant.
Right, so they should be detectable by looking at the entropy, at least some subleading contribution, I don't know in which limit, of some black brain solution in a higher dimension, like 6 or higher.
Yeah, so a good place to look is in 5 dimensions, where these objects are naught branes. So if there are these naught branes, there's a question about whether these magnetic naught branes should contribute to the entropy of a black hole in 5 dimensions. And so if you had a black hole which carried these charges, then these objects should contribute to the entropy. So I would expect that to be the case, yes. And it's an interesting question is whether anything which is been discussed in the literature would rule that out. And as far as I'm aware, that wouldn't be the case. I mean, much of what's done is based on the solutions that we know about, based on the kinds of charges that we know about, which could be addressed from the context of supergravity. If there's other things which can't be written in the language of supergravity, then I'm not sure that those would be ruled out, because these would be things which couldn't arise as supergravity solutions, but would arise from some other framework. But I think that's a good question.
Yeah, thank you.
Any other questions?
I'm sort of racking my brains about why we normally insist on getting rid of Dirac strings. And I thought there was an argument that you could get, if you left them in, you could get an Aharonov-Bohm effect as you go round the Dirac string, but then you can flip it. So it's inconsistent if you leave it in.
Yeah.
So,
So that's
what do you do?
So that's depends on whether you've got fundamental electrically charged particles.
Yes, indeed.
So exactly. So a key question is if you take an electron around a direct string in electromagnetism, you get exactly the effect you're talking about. But it turns out that the kind of things which would be which are charged with respect to this graviphoton that I was talking about. There aren't things which are electrically, that doesn't correspond to the normal mass. So the usual spectrum of things we're talking about are not charged in the way that they would. So in other words, taking a conventional particle, I think, would not, around these direct strings that I'm talking about, I think would not give our enough Bohm effect.
Would it be a momentum mode on the compact direction? Because that's the electric charge. So you'd have a PP wave in. Yeah, I mean, I don't know how a parallel transport a PP wave, but something like that.
Yeah, so it's a very good question, and I think, I mean, the key question is whether there are objects carrying precisely the charge that we're talking about, and I think the point, one way of saying it is that the way a massive particle couples to the graviton is not as an electromagnetic coupling to this vector field which comes up that we're talking about. If you had a particle which coupled that way, then that would happen. But the way that the particles that we know about coupled to the metric is not that way. They pick up the action gives you the proper length of the particle, and it doesn't have a minimal coupling to this graviphoton. And so in that sense, they don't seem to carry that charge. And so it's an interesting and important question that, but it seems that there isn't a problem which arises that way. That's something which I'm continuing to think about. But I think at least in the linearized theory, I think that there isn't an issue that way.
Okay, any other questions?
Standard Dirac quantization for that we care. But here, I suspect there's some high asymmetry from which these things are actually charged on. Right? So because the currents that are involved here have more index structure, so there is certainly high asymmetry that allows for these to exist. So relating to this question, so in ENM, when I'm forced to go from the electric or the magnetic frame, I also see emergence of new symmetries in the IR, in the magnetic frame, which I don't see in the electric frame. And this is a thing that occurs specifically when I have either magnetic or electric charges, right? So we have these higher form symmetries that appear. So these things should appear here. Have you seen them? Have you discussed them?
I mean, the kind of examples which I think you're referring to are the ones which would arise in, for example, in Yang-Mills and so on, with less supersymmetries.
Yes.
Whereas the analog of what I'm talking about here is really n equals 4 supersymmetry, n equals 4 super Yang-Mills, where I think what you're talking about doesn't happen. But there is all sorts of other structure, and a lot of rich structure which does arise there, and I think and analogs of a lot of those things should play a role here.
Okay. Thanks.
But I think the sort of the difference between the infrared and the IR and the ultraviolet is something which I think the sort of phenomena you're talking about are things which you often see in theories with less supersymmetry. For n equals 4. Yeah, so all of these, yeah. So you're talking about the generalized symmetry story. Yeah. So in the last year, there's been some interesting work on generalized symmetries for the free graviton, and they don't involve higher forms, but they involve tensors with exotic structure. And some of that story is deeply related to what I've been talking about. And so there's an interesting story which goes on there, and we can talk about that privately. Yeah. Yeah. So in the context of the free theory, then there is all that structure, and there's a very interesting question about what, if any, of that extends to the interacting theory. Okay, thank you.
Okay, let's thank. We're running a bit late. Sorry. Okay. Yeah, one last question.
Oh, okay, well, thank you. So one of the things that works quite nicely for the 2,0 theory is if you know the existence of a six-dimensional theory with Lorentz invariance that you compactify in a space-like circle, you get 5D super Yang mills. But as you know, because we wrote a paper on it, you can compactify it on a time-like circle, and you get a Euclidean 5D super Yang mills, which uniquely exists amongst all the theories. So is there a Euclidean version of 5D supergravity that you'd get from, say, compactifying 10-dimensional supergravity in signature 5-5?
Yes, I mean, there's, there are other signature versions of all of this, which are related to the various sort of supergravities you get from in different signatures you get from the M primed and the M star theories.
Is there a 5-5 theory? Do you remember? I know there's a 9, well, that's 11.
Yeah, so you start off in 11 dimensions in 10, 1, 9, 2, or 6, 5, and then you choose a signature on your 6 torus, and you get what's left. So, in particular, if you start off in 10 plus 1 and you compactify on 5 space and 1 time, you get a Euclidean supergravity. But given the different choices of signatures of the internal torus, if you don't mind having lots of times which are all compact, then you can get pretty much any signature in 5.
And the other thing, of course, is to do a null reduction, like I was forced to do for 2,0. So that would suggest that you could construct some weird 5-dimensional supergravity, and because you could do the linearized theory, see what you get, and then see if you can construct a non-linear version.
Yeah, I mean, as you know, there's a lot of literature on different ways of different things you can do with null reductions. And all of those you could apply to this, of course. But there's various issues with what you get from null reduction, as we've also talked about.
There's issues, but it always strikes me as it's highly non-trivial that there at least exists something you can write down with all the symmetries, and which is interacting.
Yeah, and that would be the same here, I think.
Okay, great. Very interesting questions and discussions. Thank you so much for the nice talk, Chris.
Thank you.